Okay, so welcome back. So now we have a seminar by Victor Godet from Paris. So Victor has done very important work on the connection between the Wheeler-DeWitt equation and holography. And so he will, but that's not what you are going to talk about today, no, but the Wheeler-DeWitt equation will play an important role as well. So please.
Okay. Yes, so thanks a lot, Marc, for the invitation, and I'm really honored and happy to speak here about quantum cosmology and the Wheeler-DeWitt equation. Yes, so I'm going to talk about some recent progress on these questions. So this is the plan of my talk, and I'm particularly excited by some very recent connection between these ideas and number theory. So I will first start with a review on what is quantum cosmology, and this will be, I will try to review what are the issues and a little bit what is maybe the state of the art and the recent developments. And then I will talk about the quantization of toroidal universes. So when you take the spatial universe to be a torus, and in this case, we'll see that there is a rather direct connection with the Langlands program in number theory. And in fact, we will see that these tools from the Langlands program will be very useful to study the Hartle-Hawking state. And this will reveal also some connection with the Riemann zeta function. But first, let me start with recalling what is cosmology. So cosmology is the study of the evolution of the universe. And this is the picture we have about this. So it started with a Big Bang, and then there was a period of inflation. And we have a pretty good understanding of essentially all this part here, up to today, which is 13.8 billion years after the Big Bang. But the early universe is not very well understood. And actually, the models that describe all this part here, so it's essentially after 10 to the minus 32 seconds after the Big Bang up to today, is the so-called lambda CDM model. And lambda is for the Cauchy constant, which was measured to be positive. So this was this incredible measurement using supernova in '98 that shows that we live in a DS universe. And CDM stands for cold dark matter, and with these simple ingredients, and also with the standard model of particle physics, we have a model with relatively few number of parameters, which essentially explains all experiments we have made. And this model involves classical gravity and the quantum field theory. So it does not take into account quantum gravity effects. And we expect that this quantum gravity effect actually will be important in the early universe. So this is a picture of the CMB. So it's the closest that we have to a direct picture of the Big Bang, even though it was 300,000 years after the Big Bang. And it was taken by the Planck telescope. I must say, this cosmic microwave background is just a radio wave background that is everywhere at all time, and directly comes from the Big Bang, essentially, and was discovered by accident by these two radio engineers from Bell Labs in 1965. And what is amazing about this picture is that, the background is not completely uniform. It has these small fluctuations that you can see in the picture. And these are quantum fluctuations. And these fluctuations are essentially the seed of all structure in the universe. So the reason we don't live in a uniform fluid or something like that is because of these original fluctuations. And this is just to illustrate that quantum effects are definitely important in the early universe. And so we need a theory of quantum cosmology. So basically, we need a quantum version of of this maybe lambda CDM model. Or yeah. Also, I must say, I think we have some time, so feel free to interrupt me and ask questions. I'm happy to discuss. Yeah, and then so Marc lecture is about how to define quantum gravity in the canonical formalism, and so this gives actually a way to define quantum cosmology, and so this canonical quantization is just results from applying Dirac's original prescription on quantizing a system with constraints using this Hamiltonian formulation of general relativity. And what it tells you is that the physical states of the system are the solution of this Wheeler-DeWitt equation. And this defines the Hilbert space. And the observables are just the operators that commute with the constraints. So in principle, this tells you everything you need. It defines the theory for you. But of course, things are not so simple, as I will explain. But also, we must say that cosmology is a bit different than maybe other physical theories, because in cosmology, we also need a theory of the initial state. So in addition to having the space of all physical states, we also want to know what is the states that describe our universe, what is the states we are living in right now, in some sense. And there is an interesting proposal for this, which is the Hartle-Hawking proposal. And so this was proposed in 1983 by Jim Hartle and Stephen Hawking. And the last seminar of last week reviewed this a bit. But essentially, the idea is that you can construct a particular solution to this equation by using the so-called gravity path integral, by integrating over all metrics ending on a special metric G with a so-called no boundary condition, basically the fact that the completion here is smooth. And this is a very natural state that you can define. It's, in some sense, the gravitational vacuum of cosmology. And so Hartle and Hawking proposed that this is the wave function of our universe. And this proposal is really interesting because it gives very concrete and direct predictions that we can compare with experiments. So it's not at all abstract, it's something that is very computable. Okay, so from this, you might think that all is good. We have a theory of quantum cosmology and a theory of the initial state. But of course, there are some difficulties. Okay, the most obvious one, and as Marc explained, is that we don't know how to solve the Wheeler-DeWitt equation. So the starting point, we don't even know how to do the starting point. Okay, so this is something we'll address in this talk by considering some approximations. So basically, you need some kind of approximations to be able to do something. And we will discuss two of these approximations, one being the large volume limit, and the other being just the semi-classical limit, where the Newton constant is taken to be small. But there are many other issues with quantum cosmology. So about the Hartle-Hawking state, so it's great that the Hartle-Hawking state gives us very concrete predictions, but as of now, the predictions are just not correct. And if you take the simplest model of toroidal inflation, it just doesn't predict the right thing. Then, of course, general relativity is not UV complete. So we are just doing some semi-classical or effective analysis, and ultimately we will need some UV complete description, such as string theory. And then there are all the issues that Marc discussed in his lecture, namely the fact that GR has such a huge diffeomorphism invariance, makes it very puzzling to think about even the basic questions to ask. So what are the physical observables? How to think about time evolution? All these are questions that are non-trivial. And finally, one thing that is special about cosmology is that cosmology is the only system where there is no really an external observer. So, because cosmology is supposed to describe the entire universe, the observers are inside the system. And quantum mechanics was defined by using an external observer. So this suggests that if you really want to understand, quantum cosmology and how observers are in quantum cosmology, you will need to modify quantum mechanics. And this is something that is currently an active topic of research. Yeah, so are there any questions about this? Yeah, if not, I will go to a slight tangent, also to explain some of the things that has happened in quantum gravity in the last 20 years, and I think that provides a guide for how to address these questions. And this is the so-called ADS-CFT correspondence. So for now, we have discussed cosmological spacetime, so with lambda positive, or if you want, DS spacetime. But there is a simpler version of the problem corresponding to so-called ADS spacetime, where lambda is negative. And the reason for this is that ADS spacetime have boundaries, and using these boundaries, it helps a lot to study the system. And in particular, this problem of quantum gravity on ADS spacetime was essentially completely solved by Maldacena in 1997 by the so-called ADS-CFT correspondence, which is the statement that so ADS spacetime look like a bit like the interior of this cylinder here. So the spacetime is the inside of this, and it has some boundary, which is the boundary of this cylinder. And the ADS-CFT correspondence is the statement that all the dynamics of ADS inside this cylinder is completely equivalent to a so-called CFT on the boundary. Okay, so if you don't know what CFT means, it doesn't matter. You just have to know that it's a completely well-defined mathematical system, more like a quantum field theory, which is well understood. And so this gives a completely well understood way to do quantum gravity in ADS. And so this has led to many interesting developments, and I'll just flash some of them. There are too many to review, but here are some of the lessons that we have learned from this correspondence. So the first one that is obvious actually is the fact that spacetime behaves in a holographic way, and so this is literally what the correspondence is telling you, that there is a dual description involving one less dimension on the boundary. And this was an idea that actually predated ADS-CFT. It also tells you that black hole evaporation preserve information. So this is the Hawking information paradox. And Hawking himself believed that black hole would destroy information. But since the dynamic inside this ADS is equivalent to the dynamics of the CFT, which is a well-defined quantum system, it directly implies that black hole cannot destroy information. And actually, Hawking was convinced by this argument that information is preserved. And of course, there are many more questions you can ask about this, about the nature of the black hole interior and how information escapes. And this is also an active topic of current research. So it has also told us how spacetime can be thought of as being made of quantum entanglement. Okay, so I won't discuss this too much, but this has been a major direction of research. And something that maybe really more related to this talk is the relation between quantum gravity and chaos theory. So we have learned that black holes are the most chaotic objects in nature, and that the gravity path integral seems to compute some kind of random average. So what this says is that in quantum gravity, we expect that there should be some kind of random or chaotic structure. I mean, and now what I want to ask are, what are the counterparts of this idea in cosmology, so in the DS context? So all these apply for black holes or in the ADS context. But of course, the topic of this talk is cosmology, and I will try to kind of suggest what could be a counterpart of of some of these ideas.
Victor, can you please make a comment about what the real meaning of most chaotic objects in nature?
Yes. So what happened is that there's a very simple way to understand chaos for ADS black holes using this kind of shock waves technology. And it was found that you can just compute the so-called Lyapunov exponent of the black hole. And, okay, I don't have white chalk, but it was found that the value of this Lyapunov exponent is just 2 pi times the black hole temperature, the Hawking temperature. So this was the work of Schenker and Stanford. And then 2 years later, with Maldacena, they actually showed that this is a universal bound on chaos, meaning that no quantum system can have a Lyapunov exponent bigger than this. And this is the sense in which black holes are maximally chaotic. And the reason this is interesting is that it tells you, if you want, a necessary condition for a quantum system to be dual to gravity or black holes, because you would need a quantum system that is maximally chaotic. And there have been such examples, like one example that has been discussed a lot is the SYK model, for example, which is a simple quantum mechanical system that is maximally chaotic and turns out to be dual to ADS2 gravity.
Besides that, just out of curiosity, is there a very precise mathematical statement about maximal chaos?
I would say yes. Of course, as any of these kind of physical proofs, it relies on a number of assumptions. But based on these assumptions, you would say it's a proof. It's a proof at the physical level. So they showed that if you make assumption about a quantum system, actually I can tell you what they are. It's just you assume that you have a quantum system that is near the thermal equilibrium, and then you compute some kind of so-called OTOC, so some 4-point function like this. And you assume that these V and W are simple operators, okay, in some sense. And then you can just show that if you look at time evolution of this quantity, the exponential that shows up will always have an exponent smaller than this. So this is like a rigorous proof, if you want. But of course, as any physical proof, it has many assumptions that you might try to find loopholes. Any more questions? Okay, but the reason I wanted to mention ADS-CFT before going into the meat of the seminar is because it has been a great inspiration, actually, for the theta. And this is what you might call the DS-CFT philosophy. And this is just the idea that if you take some ADS-CFT statements and you just write LADS equal ILDS, you would get some statement about DS. So of course, this is a very sketchy procedure. We don't know, it might not have physical meaning, but I think it's an interesting inspiration. And one way to think of it is as follows. So if I draw some Penrose diagram of the ADS Poincaré patch, so this is ADS, and this is the boundary. So the ADS-CFT correspondence is the statement that you have a CFT on this boundary, and the ADS partition function is equal to the CFT partition function. But now, if I do this analytic continuation, so LADS equal ILDS, what happens is that this diagram gets rotated, essentially. And this time-like boundary becomes space-like. And so now this is DS, and the CFT is here, is like horizontal now. And so now this statement translates into psi ds equals ZCFT, where psi is now the wave function, is now the wave function of the universe, namely the solution of the Wheeler-DeWitt equation, a solution of the Wheeler-DeWitt equation. And so one thing that was discussed in early 2000 was the fact that
CFT is a special CFT, Euclidean.
Yeah, so indeed, the CFT then becomes Euclidean. And actually, yeah, so in the early 2000s, Maldacena showed that you can use this to kind of write the Hartle-Hawking states as the partial function of some holographic CFT after this analytic continuation. And this can be viewed as a change of contour on the original Hartle-Hawking contour. And then some work we did more recently with Subrat Raju, Tunir Chakravarti, Joydeep Chakravarti, and Priyadarshi Paul, so at ICTS. So this is from 2 years ago. What we showed is that actually the Wheeler-DeWitt equation implies, in some sense, that the wave function is always a CFT partial function in a generalized sense. And this is a statement I want to go into more detail, so now actually I will explain a bit this derivation. Yeah, any question?
So why is ZADS is transformed into psi-ds under your analytic continuation?
Yeah, I mean, one way to see it is just that you see, like, ADS has a boundary, so the CFT lives at this boundary. But DS doesn't have boundary. So if you draw t-equal constant slice, so they would look like this here. So each of these slices touch the boundary. But here they look like this, and the time slice doesn't have a boundary, so the boundary is in the future. So this means that whatever is this CFT partial function, it's something that is quite different from this ZADS. And yeah, I know this is a bit heuristic, and I would say like all this DS-CFT philosophy stuff is not a very well-defined thing. It's more like some kind of intuition we're trying to get about the theta using ADS-CFT, and it's still something that remains to be understood. But I wanted to mention it because in some sense, I would say that the result I will present in the next few minutes, could be viewed as a more rigorous version of what you might call DS-CFT. But this is something that people debate a lot. So now I will go slightly more technical just to explain exactly what is this result. And this is again about solving the Wheeler-DeWitt equation. And because the Wheeler-DeWitt equation cannot be solved, in general, you need to take some approximation. And so for an expanding universe like this one, first of all, we'll take the limit. Yeah, we'll take the limit where the volume of the spatial slice goes to infinity. And this is the large volume expansion. And in a de Sitter universe, is the same thing as the late time expansion. And actually, throughout the talk, I will always use this spatial volume as my canonical time. So as Marc explained last week, in quantum cosmology, or in the Wheeler-DeWitt equation, there's no absolute notion of time. Time is part of the canonical variable, and you have to make a choice. You have to choose an adequate notion of time. And here, the volume plays the right role. What is important is it has to be monotonous. And now what you can do is you can just consider the following expansion. So if you expand the Wheeler-DeWitt equation around a large volume, and this can be done by decomposing the metric into a while factor times the metric with unit determinant, then you can just rewrite the Wheeler-DeWitt equation in terms of these variables and take the limit omega goes to infinity. And what you find is that the different terms in the equation behave differently, and the equation will simplify. So the way we did this is by writing the wave functional in this kind of WKB, like ansatz, where we write terms that go with omega up to omega to the 0, essentially. And then you just solve term by term. So for example, the first term goes as omega to the d, and the Wheeler-DeWitt equation for this term just becomes this equation, which can be solved. It's just a volume term. And then you can just go and solve each of these terms up to this x0. And this x0 is more interesting. It tells you something. It satisfies this equation, which is the Weil anomaly equation. It's a Weil anomaly equation. And the anomaly here is essentially the one you would get in ADS, but not analytic continue using this LADS equals ALDS. So in the case of ADS3, it was actually computed by Marc in 1986. So C equals 3 LADS over 2G become here C equals 3 ILDS over 2G. And here it's just a consequence of the Wheeler-DeWitt equation. And then I also wrote the anomaly for D equals 4. And the conclusion of this analysis is that...
I have a question concerning the expansion. So the very first term you wrote, it corresponds to dropping which term in the Wheeler-DeWitt equation, which term is subdominant in the leading order. The curvature is subdominant?
Yeah, the curvature is subdominant. So indeed, so the dominant term is the Cauchy-Miller constant.
And the kinetic term in the...
And the kinetic term. And actually, this is why this technique only works for lambda positive. Or at least it doesn't work for lambda equals 0. Yeah, but yeah, indeed, the Cauchy-Miller constant is dominant. But then this second term here, x d minus 2 actually, will involve the Ricci curvature. And you can also generalize this to matter, to like we did it for massive scalar fields. But yeah, so the punchline of this analysis is a bit something like this DSCFT ideas, namely that the fact that the late-time solution is always, in some sense, a CFT partition function. But this is just in the sense that it satisfies the same word identities. So it's, if you want, what we're really saying is that the wave function here has the same symmetries as the CFT partition function. And yeah, so for CFT, usually you might think of additional constraints, but here we don't impose any of them, just the symmetries. But it's a nice way to think about it, and it tells you that the Hilbert space, at least at future infinity, is really the space of all CFT partition functions. And just to tell you that this idea is not completely empty, I wanted to mention a rather recent result, namely just an example of such a CFT. So you can take, yeah, so first of all, I must say, these CFT are kind of exotic because in some sense they must be in L2, so they must be square integrable if you think of them as wave functionals. And usually CFT partition functions are not. And also, this anomaly condition is kind of weird because it tells you that the central charge is imaginary. But there is a way to get such CFTs by taking non-CFTs at analytically continued values of the parameters. And in particular, if you take the Liouville CFT2, at this value of B, you can get this value of central charge. And this state was studied recently by these people in the context of the so-called complex Liouville string. And what they showed is that some cosmological observables in this state, so this is a state for DS3 gravity, what they showed is that some cosmological observables are computed by this matrix model that computes the complex level string amplitudes. So this is just to give an example, and now actually I will go so this is this is all I wanted to say about more this kind of review section. So if you have any more questions, feel free. Okay, but so now I will go into some work I did more recently, and this is about these toroidal universes. And so here, again, we will try to solve the Wheeler-DeWitt equation, but now in a different approximation. So this will be the mini-superspace approximation. And one way to think of it, I think the way I prefer to think of it, is that so if you write the metric in this Hamiltonian form, you can use some kind of WKB ansatz for the wave functional, where at leading order in G, this leading term only depends on the constant part of the metric. So it doesn't evolve. So here, G0 doesn't depend on U, on the spatial coordinates. And then, at leading order in G, what you find is that this Wheeler-DeWitt equation becomes just a Klein-Gordon equation. And so this is equivalent to the mini-superspace approximation. But the reason I like to think of it this way is that it suggests that you could correct it order by order in the same way as before, even though here I suspect it will be more complicated. There are more ambiguities. But anyway, I will just discuss this mini-superspace approximation here.
What is capital M squared?
Yeah, so capital M squared is the mass of the particle. Okay, it will be defined in the next slide. But yeah, actually I should have defined it before. But yeah, so let me set up some notation, like how I will parameterize the spatial metric, and so basically I want to parameterize it using this variable t, which is the spatial volume, and then a variable z, which lies in the so-called generalized upper half plane. And so this is this space, essentially SLDR by SOD. And for d equal 2, this is well known. It's just the upper half plane. And usually we write tau equal x plus iy here. But for d equals 3, we can have something similar. And these coordinates are given by x1, x2, x3, and y1, y2. And this is the so-called Iwasawa decomposition of GLD, and it gives the most standard coordinates for this space. And then explicitly, the spatial metric is like this volume term times a metric with unit determinants defined as z times the transpose of z. So and so in this mini-superspace approximation, the nice thing is that cosmology becomes a very simple system, namely just a particle. And the simplest way to get this is just to start with the gravitational action. So this is the Einstein-Hilbert term and the Gibbons-Hawking-York boundary term. And if you just evaluate this action on this ansatz, on this metric here, you get the action of a particle, and m is the mass of this particle. So it's essentially 1 over g up to some coefficient. And this is not at all surprising. It's just what you're doing is just Kaluza-Klein reduction on the torus. So the full space-time is the torus time, and you just do Kaluza-Klein reduction on time, so you get a particle. And this is a particle on this DeWitt mini-superspace, which can be described by these two coordinates, t and z, that I introduced before. And then also what you get from this is you get the metric on this space, which look like this. It's like this. So t here will be like our canonical time. And you see that it's also the right time for this particle. And I must say that I would say that this was already known by DeWitt. So in his original paper, he wrote down this, essentially. He wrote down this space, and he actually studied geodesics in this space. But it has not been studied very systematically, and this is what I'm going to do here. Yeah, so here this was for general metrics, but now we will focus on a special case, namely the torus topology. So the torus topology corresponds to just taking these spatial coordinates to be periodic. Right? And the nice thing about this is that there is an additional gauge symmetry when you do this, because there's some subgroup of this SLDR symmetry that acts on Z, which is actually part of the spatial diffeomorphism. And this is because if you act with SLDZ on this U, it preserves this periodicity condition, and it's part of the mapping class group. So you should caution by it. And this implies that the Hilbert space for this particle, which is also the Hilbert space for this mini-superspace quantum cosmology, is just this space. So it's L2 of this upper half plane, general upper half plane, mod SLDZ. And this is a space that has been studied by mathematicians for about 50 years. It's known as the space of automorphic forms. And it is in some sense the main object of study for the long-length program for GLDR. And mathematicians have developed very powerful tools to study this, and we will see that they are very useful here. But I'm going to review some of them. Let's see. Yeah, so first, let me give a more concrete explanation of these spaces. So for D equal 2, it's H2 by SL2Z, and this is known as the modular surface. So here, SL2Z is just the standard action on the upper half plane, which is the same as H2. And so here, if you draw the upper half plane, what you have is that SL2Z tells you that you have maybe some fundamental domain here, and this fundamental domain is mapped by SL2Z to copies of it, and you should only consider only one copy. And in particular, the volume of this quotient is then finite. And this is one very important thing that makes the torus especially nice. And so for D equals 3, you have something similar. So now H3 is a 5-dimensional space. It has 5 coordinates, and SL3Z acts in a quite similar way. And the volume is also finite. And this is true also in general dimensions. So of course, D equal 2 corresponds to pure 3D gravity, and D equals 3 corresponds to 4D gravity. So D equals 3 is the most interesting case, I would say. But D equal 2 is a very useful case to understand. And I will draw some of these pictures in this upper half plane. And so one of the major tools that was developed by mathematicians in the study of these spaces are the so-called spectral decomposition. And the spectral decomposition basically gives you a basis of this Hilbert space. And it gives you a basis that, in some sense, respects the symmetries. So the point is that this particle has this SLDR global symmetry. And you want to have a basis which diagonalizes this symmetry, or diagonalizes the Casimir of this algebra. So for SL2R, for D equal 2, there's only one Casimir, and this corresponds to the Laplacian on H2. And the decomposition was obtained by Selberg in 1956. And so it takes the form of a constant plus a continuous spectrum in terms of this Eisenstein series, and a discrete spectrum in terms of these mass forms. So you don't need to know what these are in detail, but you must, yeah, they are very precise mathematical objects. And for d equals 3 and higher, the theory was obtained by Langlands. So Langlands obtained the general theory for any of this Hilbert space as long as the volume is finite. And here I wrote the case of d equals 3. So it's very similar. You also have a continuous spectrum and a discrete spectrum. Just the continuous spectrum is a bit more complicated with this so-called minimal parabolic Eisenstein series and the maximal parabolic. But the point is that these decompositions are really relevant for quantum cosmology because they are literally the right basis to study the problem. And these objects are called in the mathematical literature as automorphic representations. And this is just the idea that they are not just automorphic forms, but they are automorphic forms which are eigenfunctions of this symmetry, of this symmetry algebra. And so here we see that they are essentially the physical state of quantum cosmology on the torus.
So they are somehow a basis of solution of the Wheeler-DeWitt equation, or they give us a basis of solution?
Yeah, in some sense, they are a basis of solution of the Wheeler-DeWitt equation. Even though I would say that here it's a bit trivial in this minisphere approximation because, for example, in d equal 2, the only thing it tells you is that you have a SL2Z invariant function. So it doesn't, by itself, it doesn't address the difficult part of solving the Wheeler-DeWitt equation. Actually, it's more a solution of the momentum constraint because this SLDZ invariance is part of the spatial diffeomorphism group. But yeah, so in the mini superspace approximation, the Wheeler-DeWitt equation is simple, and then it gives this. But it's true that these tools are only, for now at least, in this mini superspace approximation, and it's not clear whether they could be useful in more generally. I don't know. Yeah, so I'm referring to mini superspace.
Also, you could say that it's any function. So this is the harmonic analysis. The question is, do you need the harmonic analysis? So is it useful at the next order to know the...
Yeah, I will argue that it is, because since the mini superspace approximation, for me, is the leading order answer, I would expect that you can just start with this and then try to correct it. So in that sense, it should still be useful. But since I'm not sure about that, I'm only focusing on mini superspace.
But it's a leading order of an expansion. Let's see. So this first approximation, you drop the spatial curvature essentially, because you are on the torus and it's homogeneous.
Yeah, I would say yeah. But you drop much more than this, I think, because essentially what you drop is, so the functional would be like so basically instead of considering the wave functional to be a function of like the whole metric on the torus, you basically reduce it to a function on just a finite number of variables. Yeah, so here you have an infinite number of variables. So, of course, it's always a bit tricky to do these things.
But this is not equivalent to assuming that the metric is invariant for translations, and so that there is only one finite set of variables if it's homogeneous.
Yeah, if it's homogeneous, it's probably equivalent to the fact that it's constant. Yeah, it's homogeneous, indeed.
And T and Z just parameterize a symmetric, a metric.
Yeah, it parameterizes a constant metric on the torus. And you see, the reason I think it might be right that it's because if you write it as let's say some function of T and Z divided by G, And then you might have a function, so f0, and then you might have a function f1 that depend on the full metric. So at least if you take these ansatz, yeah, I think you would be able to correct it order by order. But then you might ask why to take this ansatz. Not sure. But yeah, yeah.
So the leading order formally would be like strong coupling. I mean, G goes to infinity.
No, it would be G goes to 0 here.
Yeah, sorry, okay.
Yeah.
That's strange. Okay.
Yes, so actually one thing that makes me optimistic is just the fact that so the previous thing I discussed, this large volume expansion, we had the structure like this, and there it was at least possible to solve for some of these terms up to the constant term, and this looks similar, but of course it's more difficult once you have infinite number of variables. Yeah, and then then I also wanted to discuss a bit the third quantization idea, because the nice thing once you have the fact that quantum cosmology is just the theory of a particle, so it's the word line theory of a particle, then this third quantization becomes very simple. So first of all, third quantization is the idea that maybe we should not consider just a single universe, but you should allow for states containing a multiple number of universes. And this was an important part of how quantum field theory was discovered by understanding that this was the right thing to do for particles. And so more concretely, what you should do is view the wave function as a field operator, and then its modes are creation and annihilation operator for universes, and you can build a Fock space out of these modes. And so here it's very concrete, because since mini-super space quantum cosmology is the word line theory of a particle, then this third quantized theory is just this free scalar field. So this is a free scalar field on the space. Yeah, let me write the space. It's essentially this space, so it's this mini-super space. But of course, we also have this SLDZ quotient, since we are on the torus. And because of this SLDZ quotient, we have to use this long spectral decomposition. So this is also the right basis for this, because it is the basis that diagonalizes the time evolution. So time evolution here is governed by the Klein-Gordon equation, which is the same as the Wheeler-DeWitt equation. And the Klein-Gordon equation involves these Laplace operators that, and these bases are precisely eigenfunction of these.
So chi are just the Fourier mode determined by each time the eigenvalue of the Laplace operator.
Exactly, yeah. So chi is just whatever you need, so that this is solves the Klein-Gordon equation. And and then what you get is just a Fock space built on this annihilation and creation operator, A. And something that I think might be interesting in the relationship with number theory is the relationship between the relationship to trace formulas. Yeah, so first of all, this third quantized theory is quite interesting. You can study this third quantized trace tensor, and this tells you, there are many interesting observables to study. Like the simplest one being just the Hamiltonian. So if you integrate T00, you integrate it on a, distance T, on a constant T slice, so T equal constant. It defines a time-dependent Hamiltonian. So this is a system which is time-dependent. But you can also compute SLDR charges using it. And then in physics, we have this equivalence between the first and second quantization of the particle. So, you know, for example, the green function, just this two-point function here, you can either think of it as literally a two-point function in QFT, or in the word line description, it's like an integral of a particle path. And so this integral here we localize on geodesics, and this part here is a spectral is kind of a spectral side, and so this is essentially a trace formula. So it has a spectral side and a geometric side, and here the geometric side, of course, in the particle description, it's the sum of a particle paths. But since these particles are literally describing toroidal spacetimes, this is also the gravity path integral. So you're summing over cosmological spacetimes, in some sense. And the reason I'm mentioning this is that trace formula are one of the major and most powerful tools in the long-range program. And okay, I won't have time to explain this, but for example, the Kuznetsov trace formula gives a way to compute the exact norm of the Hartle-Hawking state that we will discuss in the d = 2 case. And this is the formula that you get, which shows a lot of structure. Yeah, and then I want to go on the Hartle-Hawking state. So are there any questions about this?
So you define a correlator here. How do you want to interpret it? You want the evolution of a universe to another?
Yeah, exactly. So this is so yeah, basically you start with some tori here, and the tori is labeled by this T and Z. So T is literally the volume, and Z is like the complex structure, if you want. And then you want to end on a different tori, which is T prime and Z prime. And what you're summing over is basically all the spacetimes that interpolate between the two. And if you, and of course, in the mini-spatial approximation, this sum is the same as a particle, as a particle sum, because the particle. Yeah. But it's just interesting that it gives a kind of interpretation of the gravity path integral as really computing the geometric side of a trace formula. But okay.
Maybe a comment question. So you say this is somehow a small g approximation.
Yeah.
It's very different from linearized gravity.
Yeah, I guess it depends on which background you linearize.
Okay.
So yeah, of course it will be different from linearized gravity around Minkowski, or around de Sitter, but in some sense it should be some type of linearized gravity. Yeah, yeah. I'm not. No, I guess the thing is that it's. Yeah, it's more about the dynamics of the moduli of the torus rather than the. So I cannot discuss gravitons or anything like that.
Especially in d = 2, there is no gravity.
Yeah, in d = 2, there's no gravitons, but even in higher d, I just cannot discuss them. I mean, but and I would expect them to show up at higher orders.
You're an approximation or you're an origin.
Exactly. I'm an approximation where I neglect them. Yeah. Okay, so now in the last part of this talk, I will discuss the Hartle-Hawking state and how these tools can be used to compute and study the Hartle-Hawking state on the torus. Yeah, so first of all, let me recall what is the Hartle-Hawking state. So it's just obtained by fixing some torus at infinity. So here you take the limit t goes to infinity, and then you only have this z variable. and then you have to find spacetime which end on it and have no boundaries. And these spacetimes are very simple. They are just the filling of the tori. So they are just the inside of the tori, if you want. And you can describe them very explicitly by this metric, for example, and then you can just solve Einstein equation. And so here you just solve Einstein equation and you impose the no boundary condition. So this is basically what you want is, so the torus is like a product of d circles. What you're doing here is you're just replacing one of these circles by a disk. So the field tori is just a disk times d minus 1 circle, and so the no boundary condition is that you have a smooth center at the disk. And if you do this, you'll get a unique solution, and this is the contribution that it gives to the path integral. So this is like the classical action, if you want, and it goes as 1 over g, and multiply this dead z in this variable. So yeah, so dead z, for example, dead z is like this y variable in d equal 2, and in d equal 3 it's y1 square y2. Yeah, so it's and then you can get this this c here, and I wrote the value for d equal 2 and d equal 3. And this has a kind of periodic phase with the dimension, and note that in d equal 3 it's particularly nice because c is positive, so this sum is actually. Oh yeah, sorry. What?
Is this an expansion at y large or y2 y?
No, it's not. It's just. Why are you asking this?
Because I saw the y were the coordinate on the torus complex vector. So it's you're supposed to do modular invariant when you're right.
Yeah.
And this is very not.
Yeah, exactly. So no, I haven't finished. Yeah, indeed. So this is just one of these non-binary geometries, but of course you would need to sum over all of them to get a modular invariant function. This is the next slide, actually. But yeah. So.
Solving the equation assuming a dependence only on the y variable, and then you find the character somehow.
Yeah. So basically, the point is that when I'm solving this equation, I have to choose one circle to close, and here it's actually the last one that is closed, and so I get one of these solutions. But in general, you would have to sum over all of them. Oh, sorry. Yeah, so you have to sum over all these solutions. And the point is that what you have to sum over is all the way to fill the torus. So for example, if you have a product of d circle, what you can do is you can pick any of them to close, to fill, but you can also pick a linear combination of them where n1 and d are integers. And you need the condition that the GCD of n1 and d is 1. So you need the circle to be primitive, because otherwise it will produce a conical singularity. So essentially, you can write the Hartle-Hawking state here as a sum over z to the d with this condition.
There is no dominant contribution, or all of them are of the same order?
Yeah, it's not clear. Maybe in some regime, but I would think that you really need to consider the full sum. And the nice thing about this sum is, I mean, yeah, we'll see that you can compute exactly the full sum. So. And now one thing to say is that, yeah, so you can write this sum in this way, but you can also write it in the following way. So it's also a sum of this coset where P is the maximal parabolic subgroup. So this is just because this coset is in bijection with this set. Yeah, and also I should comment that this is exactly the same sum as the so-called Maloney-Witten partial function in ADS3, because you can also consider a similar problem in ADS, and it's the same sum. So actually, everything we do can also be applied to ADS. The only difference is that the value of C will change. But anyway, we should define this sum for positive C and then, in some sense, analytically continue in C. But yeah.
Is it convergent?
Yeah, so it may not be. But this is the thing. So in D equals 3, because C is positive, it's convergent, actually. So you would say in the most interesting case, it's convergent. In D equal 2, C has a phase. So naively, it's not really convergent, but you can define it by regularization. Okay, I will discuss this more. But I think the right thing to do here is always to do it, in some sense, for general C, and then to do whatever computation you want to do with this state, and at the end, analytically continue in C. And this gives a finite answer, usually. Yeah, and I wanted to mention also another interpretation of these no-boundary geometries that is particularly clear for D equal 2. So since we can think of cosmology as a particle, these geometries are just trajectories of this particle. And here there are trajectories on this space. And for D equal 2, it's known as Harton's billiard. And so this gives you some quite intricate billiard trajectories that are also related to this idea of cosmical billiards.
So this is PGL2. Did you choose it by purpose?
Yeah, indeed, there's a Z2 quotient, yeah. And now let me tell you how to compute this Hartle-Hawking state. So actually, it's very simple once you know, once you have this spectral decomposition. And so the reason is that so one object that appears in the decomposition is the maximal parabolic adjunctant series, which is a sum that is very closely related to the Hartle-Hawking state. And you can see that the relationship between this sum and the Hartle-Hawking sum is just some integral transform, namely the Cahen-Mellin integral, just this integral. And so this gives a way to write the Hartle-Hawking state in terms of this Eisenstein series. And this is actually the spectral decomposition of Hartle-Hawking.
So you mentioned earlier that the spectral decomposition is more complicated than that. So does it seem that your approximation missed the cuspidal spectrum?
No, it's just that at leading order, you only get the constant and the maximal parabolic adjunctant series. But indeed, at higher order, you would get actually contribution from the cuspidal spectrum and other things, actually. I mean, yeah. But yeah, indeed, at leading order, it's especially simple. So in this meaningless approximation. But actually, higher order correction can be discussed in terms of the G function. But okay, I won't have time to discuss them here. So in D equal 2, they can be computed exactly. And in higher D, you might try to do something similar with this G function. But now, I want to emphasize that so this spectral decomposition is really like, it's really a computation of the Hartle-Hawking state. And it is the main thing that, it is the main thing that, I will discuss some of this implication, the implication of this formula. But first, I wanted to review the Riemann zeta function because it will play an important role in the next few slides. So the Riemann zeta function is just defined as this Dirichlet series, which can be analytically continued using this functional equation. So you define the so-called completed zeta function, and it satisfies this equation. And the important thing about it is that although it has trivial zeros, it also has non-trivial zeros, and they are conjectured to be on the line with real part 1/2. So this is the Riemann hypothesis. And also, let me mention that these imaginary parts are very mysterious. And they are conjectured to be eigenvalues of a hypothetical self-adjoint operator known as the Hilbert-Polya Hamiltonian. And the reason we believe this is that if you look at the statistics of these numbers, they satisfy basically the same statistic as the eigenvalue of a random Hermitian matrix. And of course, one of the reasons some mathematicians have tried to construct this operator is that the hope was that constructing such operator would help in proving the Riemann hypothesis.
So you could prove it, actually.
Yeah, exactly. It might prove it. Yeah.
So it's just Hermicity, reality of the eigenvalue of the Hermitian.
No, of course, but no, I agree. Yeah, okay, yeah. If you, but okay, then the question is how to construct the operator. But
yeah, but if it's true, it's
yeah. And now the reason it shows up here is for the following reason. So it's so maybe I should explain this a bit. It's the fact that so I'll just. Yeah, I'll just write again the integrals that appear in the Hartle-Hawking state. So it's just the Cahen-Mill integral. So you just get a gamma function, and then I'll just write it like this, and then this Eisenstein series, roughly like this. And now what I'm doing here is just I'm looking at the poles of this integrand. And these Eisenstein series here have poles actually at the location of the non-trivial zeros of the zeta function. And the reason is that the object that is well behaved is the completed Eisenstein series, where you multiply by the completed zeta function. And this object here, this was actually proven by Selberg for d equal to and Langlands for higher d. This object is meromorphic, and with only poles at s equals 0 and 1. And so what you should do is you should rewrite ES in terms of this completed Eisenstein series, and so this is what I did here. And this is the reason why you have a zeta function in the denominator. And so you have poles at the location of the non-trivial Riemann zeta zeros, and also at this location, corresponding to the gamma function on the top. And so if I draw the structure of the poles, it looks like this. So in this S-plane, so you have a pole at s equals 1, corresponding to the constant term, actually. And then you have a pole at 3/2, 5/2, 7/2. So these are the gamma poles. And then you have these non-trivial zeros, which are at 1/2d. So the critical line is somewhere here. And then you would have these non-trivial zeros. I'll just put them like this.
So the integral contour is just 1/2 plus IR.
Is that what?
The integral contour, which you wrote 1/2, means 1/2 plus IR, like you are integrating over the...
Yeah, exactly. Yeah. Of course, yeah. So 1/2 is here. And then the contour I'm integrating over is this one. So here it's 1/2, and here it's 1/2d.
So by default, you mean you are doing some Cauchy circle to approximate?
Yeah, exactly. So now I'm just saying, since I have this contour in the middle, I will get two different expressions for Hartle-Hawking by summing over each side of the contour. So on this side, you get a kind of sum, an integer sum if you want, and on this side, you get a sum over these zeta zeros. And these are the two sums I wrote here. So this is the integer sum, and this is the sum of zeta zeros. And one thing to note is that this sum is actually something that you could have derived from the start, because it's just what you get if you expand the exponential. If you just expand e to the minus c det z, you get a sum of a det z to some power, and this is the Eisenstein series. But in some sense, this sum is not so interesting. It's not so convergent also. and the reason it's a bit weird is because we call that C is 1 over G. So it's an expansion in 1 over G rather than an expansion in G. And yeah, so this sum is more interesting, and it tells you that the Hartle-Hawking state is a constant term.
Approximation is at small g.
What? No, I'm always in the limit G goes to 0.
Yeah, yes, so the expansion in 1.
No, so expansion 1 over G is quite bad. It's like asymptotic expansion.
It doesn't mean anything.
I wouldn't say it doesn't mean anything. It's like asymptotic expansion.
Well, I mean, if you start from an approximation which is valid as small g, you can't expand it large g.
Yeah, exactly. So I agree. I mean, but this is like a formal equality, if you want. But I agree that. Yeah, I will show some numerics if I have time. How much time do I have? Okay. Yeah, I have time. But yeah, so let me just say, so this shows that this Hartle-Hawking state can be viewed as a constant plus some small fluctuation on top, and these small fluctuations are controlled by these non-trivial zeros. And actually, the Riemann hypothesis tells you the scaling with G, because C is 1 over G here. So in D equals 3, it tells you that, yeah, it tells you that psi HH is something like 1 over G to the half plus G to the 1/3, essentially, times some fluctuations. And actually, yeah, this is some numerical plots. So here, I'm just summing the first expansion for 200 terms or something, and for d equal 2, so this is in the upper half plane. And you see that it does converge in a quite big region, but it's also because I took a value of g that is quite large. I think g equals 0.2. And if I took smaller g, the region would be smaller. And you can see that okay, there is some structure. It seems to give some wave function. And actually, in this case, yes, something I want to emphasize is that we don't really need psi HH to be convergent, because psi HH is the wave function. The wave function is not an observable. Observables are like what you get if you compute psi HH with the expectation value in psi HH of some observable. So, for example, the norm. And the norm is actually finite after some suitable regularization again. So what I mean is that we should not worry too much if some of these expressions are divergent. And actually, so now let's look at the other expansion, so the zeta zeros expansion. So this is the exact expansion. So here so it's an infinite sum over these zeros. And these are the first two zeros, their contribution. But now this sum is actually divergent. So it doesn't converge. And the reason is that there's this factor of I here. And this factor of I gives some exponential enhancement in some direction when you sum over all these imaginary parts. So it's a divergent representation where you have like, it's still a small contribution compared to the leading term, but it's a divergent sum. And this is because C is imaginary for d equal 2. And note that actually for ADS3, C is real. So for ADS3, it gives a convergent expansion. So it would be a convergent expansion for the Maloney-Witten expansion, partition function. But actually, the case we're interested in is d equals 3. And d equals 3 is better. So in d equals 3, you have, so here I wrote again these two expansions. So this is the expansion on the zeta zeros, and this is the expansion on the Einstein series, but I took the constant Fourier mode just to be able to plot something. And here you see that, so the blue point here is the second expansion, and it's convergent in this region, but not everywhere. And what is nice is that you can see that in the region where it's convergent, it does reproduce this other expansion, because this other expansion is this constant term plus a sum over the zeta zeros. And now this sum is actually convergent because C is real. And you can just compute it numerically.
It's only the minimum that shows up for some reason?
The what?
Maximal parabolic Eisenstein?
Yeah, so here it's just the maximally Eisenstein because, yeah. And now let's go back to d equal to. So for d equal to, what I told you is that you have this some representation of Hartle-Hawking that is actually divergent. But there's something you can do to get a convergent expression is by going back in time. Because the point is that for now we have discussed the Hartle-Hawking state in the limit where t goes to infinity, right? But you can actually evolve it back in time just by solving the Wheeler-DeWitt equation. So in d equal to, it's very simple, it just takes this form. And the Hartle-Hawking solution for any t, it looks like this. So these chi are like Bessel functions, essentially. And you can define this renormalized wave function, which is such that when you take the limit t goes to infinity, you get the HH, the previous Hartle-Hawking state. And this procedure here is really the way quantum cosmology gives dynamics on the space of atomic forms. So it's not just, so quantum cosmology is not just about this Hilbert space, but it also has some dynamical equation, namely the Wheeler-DeWitt equation. And this is the sense in which quantum cosmology can be thought as automorphic dynamics.
So this capital T is related to the volume.
Yeah, it is the volume. It is the volume. Sorry, it's the volume.
So when you go backwards in time,
So,
it's zero volume.
Exactly. So what I want to say is that so this what I call the singularity is really like a Big Bang singularity, and the spacetime they look like this. So that it's like a toroid, and then as you go back in time, the volume decreases, and then it goes to zero here. So of course you might expect that semi-classical gravity is not valid anymore here, but okay, let's just trust it. And so if you do that, then you can write down this near singularity expansion, and it looks like this. So the constant term is still there, actually. But now this part has simplified a bit. And what you see is that if you redefine a time variable to this little t here, what you get is a wave function that oscillates exactly with frequencies given by these imaginary parts. And so this is where you can connect to this Hilbert-Polya Hamiltonian. It essentially tells you that the Hilbert-Polya Hamiltonian is the time evolution operator near the singularity in the Hartle-Hawking state. And actually this statement is more general because it just follows from this expansion on Riemann zeros and the fact that the evolution is always given by these Bessel functions. And so you might hope that toroidal quantum cosmology will give a real dynamical realization of these zeta zeros. And that, so it's the Hilbert-Polya operator really shows up here in some sense as the Hamiltonian near the Big Bang. And actually, you can look a bit what it looks like. So this flickering piece, so the one which sums over zeros, is actually convergent, and the contributions are decreasing with the zeros. So it's dominated by the first zero and its conjugate. And so this flickering piece oscillates essentially in a two-dimensional Hilbert space at the frequency of the first zero, which is 14.13. in this variable t. Yeah, and actually I wanted to show some animation of this so that you can see these oscillations. Let's see. Yeah, so okay, it just looks like this. You know, it's just like a periodic. It's a periodic movement. Oh yeah, and finally, I want to switch gear a bit to discuss a different way to interpret this. But okay, are there any questions about this? Yeah. So the last thing I want to talk about is the interpretation as a Mobius average. So here, let's go back to this spectral representation. So what we discussed for now is the fact that because you have a 1 over zeta here, you can expand it on the zeta zeros. But there's a different interpretation, which is based on this Dirichlet expansion of 1 over zeta in terms of the Mobius function. And okay, I will review what is the Mobius function, but if you just plug this in, you just see that it gives an expression of the Hartle-Hawking states as a Mobius average. So it's literally a Mobius sum of some function here, and this function can be seen that this function is a CFT partial function. So this connects a bit with the discussion at the beginning. And so this CFT partial function can be computed explicitly from this Miller integral, and it takes the following form. So it's a sum of a z to the d of some function of this quadratic form. And at leading order, you can identify this CFT to be the Liouville CFTD. This is just by matching the action. So the Liouville CFTD is defined. I mean, it's defined as a generation of the Liouville CFT2. And if you compute its partial function and TD, so it's really the compactified Liouville theory here. You see that it actually reproduces this Q to the D over 2. Okay, so I haven't tried to reproduce the one-loop term, but at least at the level of the classical action, it seems that this CFT is the Liouville CFTD. Yes. So let me say a few words about this Mobius function. So the Mobius function is some very simple function. It's just defined as -1 to the k if n is a product of k distinct primes. And despite this very simple definition, it shares a lot of properties. It has the same statistics as random sequences. And so it is pseudo-random. And the lack of correlational structure in this sequence is a rather important fact about primes. For example, the Riemann hypothesis is a statement that the partial sums essentially behave as a random walk. And then there are additional conjecture like the Mobius randomness hypothesis, which says that summing μn against any low complexity function should give, in any such sum, mu should behave essentially like a random sequence. And the reason I'm mentioning this is that I think this connects. Oh yeah, there's also, okay, this is more speculative, but you can also try to write the Hartle-Hawking state on the sphere as a Mobius average. So this is something you can do with this identity. So okay, let me not. Maybe I don't have time to go too much into details, but this is not a real derivation. It's more like an analogy. So just because on the torus we had this expression as a Mobius average of the Liouville theory, let's try to do something similar for the sphere. And it turns out you can do it using this identity. But and for the sphere, it's related to the de Sitter entropy, because the Hartle-Hawking state on the sphere is e to the s over 2, e to the sds over 2. And again, this is just because the Hartle-Hawking standard sphere, if you compute its norm is just computed by the SD plus 1 saddle point, which compute the de Sitter entropy. But anyway, this is just a suggestion, and another suggestion is the following, is the fact that since the Mobius average, since we are finding this Mobius randomness structure in the Hartle-Hawking state on the torus, perhaps it's more general. So for example, in the gravity path integral, we have this lack of factorization. So here it manifests in the fact that the Hartle-Hawking state for a disjoint union of sphere is not the same as the product, even though it would be the same for CFT partition functions. And so if we understand this better, this could give prediction for this type of wormhole contribution. So these wormhole contributions are the reason for this difference. And if it's true that the Mobius average is responsible for this, it gives direct prediction for the values of these wormholes. Okay, so let me conclude. So I have, first I wanted to talk about the relationship with number theory and the Lagrange program. So we have seen that the relationship with the Lagrange program comes from the fact that quantum cosmology on TD and the Lagrange program for GLT are both about this Hilbert space and the unitary operators acting on it. And we might try to get some physical incarnation of other aspects of the Lagrange program, such as functoriality and reciprocity. But I think another suggestion is the following, is that the spectral decomposition diagonalizes the global symmetries, but there are additional symmetries on this Hilbert space, namely the so-called Hecker symmetries. And the modern way to deal with these symmetries is to go to the adels, where you add p-adic components. And we know that the right way, the real Hilbert space, the right Hilbert space to think about is this one, because this is the Hilbert space in which psi would be also an eigenfunction of the Hecker operators. And this suggests maybe some adelic generation of gravity. But I would say the general lesson here is just that we should try to use the powerful tools developed by mathematicians of the last 50 years. But now coming back to physics, of course, the end goal is to relate to our universe. Right now, we are literally in a golden age for optional cosmology with many current and planned experiments. I think right now maybe the quantum cosmology is not developed enough to really make robust predictions, but this is the long-term goal. And so let me give some suggestions. So indeed, we should go beyond mini-superspace, and we might hope that if you add matter and gravitons and slow inflation, you still have this Hilbert space, but then you have some additional tensor factor that is infinite dimensional. And then if this is correct, then you can still apply these tools in this context. And so the first question to ask would be, what are the exponential predictions of the Hartle-Hawking proposal in a realistic T3 cosmology? And does it have still this issue with slow inflation? And to address this UV completeness issue, and also this is the reason I wanted to do this analysis for general D, is that actually maybe D equals 3 is not the right choice. Maybe we should take something like D equals 9, and then 6 small dimensions, then you can embed it in string theory. Or more generally, something like M3 times Calabi-Yau. But okay, this is where I am. Thank you.